Hello, today we're going to be talking about Einstein's equation and be covering all of the tensors and the math involved to get to it. I recommend reading up on this content if you're new to this. This is not meant to be a explanation of general relativity. It's simply looking at the mathematical roadmap to Einstein's field equation. As always, feel free to leave any comments correcting me if I make any mistakes. I'm also relatively new to this. I've just studied the equations, but I feel confident I can lead you guys through an introduction at least. So to begin, we're going to need to know a few things. So we have the metric tensor, which is denoted G sub mu nu. This is just going to end in space-time. It's going to be a 4D matrix. We're going to have the Minkowski metric for flat space-time and other metrics for curved space-time. Now this also has an inverse, so Kronecker delta. And it looks like you apply the inverse which is this right here, to the metric, and you get this. Now this is essentially the identity matrix. As a note, I'm going to write this up here. The partial with respect to x mu is going to be denoted partial sub mu. So that's what this means. It means x to the muth component. Yeah. So with that, we're going to define one last thing, which is the Christoffel symbol, or the connection, if you will, symbol. Now this looks like this. It's gamma. Okay, so this is equal to 1/2 the inverse metric, and then you have partial sub mu minus partial with respect to lambda of mu. So that's what that metric, or is not metric, sorry. The Christoffel symbol, the connection, looks like. So this is talking about the curvature of space. As you can see, it's the partial of the metric. Now this itself is not a tensor because it does not transform like a tensor, but regardless, it's very important in the geodesic equation, and as you'll see in Einstein's equation. All right, so now we're going to start. Now that we have this, we're going to start here. And we have the Riemann curvature tensor. And it looks like the following. It's a bit long, but at this point, I think you should kind of be used to that. So we have 4 indices on this. So we take partial mu of gamma. Yeah. Sorry, I'm just double checking with my notes. I don't want to be consistent with my indices. Plus 2 connections up, gamma, down, or not. See, I even ran out of space. Whoa! No, no, no. Minus. Okay, so that's the Riemann curvature tensor. Big ol' mess. You're probably not going to want to compute this by hand. That's where something like Mathematica would be lovely. So we start with that, and we contract it by summing over the first and third indices to get the Ricci tensor. This is a lot shorter to write out, at least in its like summarized form. So, as you can see, we're summing over the first and third indices to contract it into two indices. Okay, and then we get the Ricci scalar, which is just R, and we get that by applying the inverse metric. Now we're missing one really important thing. So this is for the left-hand side. This is left-hand side. For the right-hand side, we have the momentum energy or the stress energy tensor. So it looks like this, and it is, I'm going to provide the full 4x4 matrix. So we have T, YY, TZZ, and then we have the mixed upper and lower. So we have TXY, TXZ, TYZ, TYX, TZX, there we go, and then TZY. So that is the full stress energy tensor. Now I'm gonna break down what these components mean. Hopefully it might get a little messy. Let me see if I'm gonna get a pen. See if this works. Ah! Red pen. Okay, this should work. Okay, so this, oh, that doesn't look too much different now, does it? Here we go. Okay, so this is the energy density, typically denoted rho. And we have a submatrix here. And this submatrix is momentum flux. And then we have this up here is the energy flux. This on the side is the momentum density. And then this diagonal here of the submatrix, this is all pressure in the XX, YY, ZZ component. And then finally, you have upper, lower. Again, this is a symmetric matrix, so these are equivalent here, right? I think. I'm fairly certain it's symmetric. There might be cases where it isn't. I digress. This upper and lower triangle of the submatrix, so I guess I'll just circle one of them. This is the shear stress. I think sometimes it's denoted with lowercase sigma, perhaps. Pressure denoted with P. This might be with phi. This might be with rho since it's density, or maybe with something else. But that's the components of the stress energy tensor. Now that leaves us with one last thing to write down, and that is Einstein's equation. Which is simply this. You take the Ricci tensor and you subtract 1/2 the Ricci scalar times the metric, and you set that equal to 8 pi g, so that's this constant, times the stress energy tensor. And that is the evolution mathematically up to Einstein's equation. So let's take a look at this. We have some supplemental information here that's just good to know. Christoffel symbol is obviously very involved. So we take the Riemann curvature tensor, which is was developed by Riemann. It's just describing the curvature of a geometry, of a manifold specifically, I believe. And then you contract that into the Ricci tensor by summing over the first and the third indices. And then you contract once, well, I don't know if you can call it contraction. I don't know, but you get the scalar by applying the inverse metric. And then from there, so we have 3 out of the 4 big pieces. And this fourth piece, the development of that, I think I'll leave to another video because I'm not sure myself. But this is what it is, and this is its components. Yeah. Again, if you have any questions or comments, please leave them below. I'll see you in the next video.